Hello and welcome to this video. Today I'm going to give you the most complete explanation I've seen on YouTube by far of why airplanes fly. I'm Sergio Hidalgo, an aerospace engineer in case you don't know me. I've already made a video on why supersonic airplanes fly, and today we'll discuss why subsonic airplanes fly. They're two completely different things. I'll link the video on why supersonic airplanes fly in the corner. The explanation of why subsonic airplanes fly will be split into two videos. This is the first, the second will follow. Discussing lifting surfaces like flaps and slats. How do they work and why do they increase lift? If you want to know why subsonic, commercial, or passenger airplanes fly, watch this video. Because there's always the usual question of, do airplanes fly because of the difference in pressure on the wing? Or do airplanes fly because they're deflecting air downward? Subscribe if you haven't already so you don't miss the next video. Let's get started. First, three things must be made absolutely clear. People often give three explanations that are completely wrong. National Aeronautics and Space Administration says so, not me. I'll leave the references below, but let's go over them. The very first one. If in your explanation of why airplanes fly, you use the typical explanation that the particle on top and the particle on the bottom reach the end of the airfoil at the same time. You're using that explanation is wrong and useless. Forget it. In fact, I have a video talking specifically about that, why it never happens and why people believe it does. It has been observed in wind tunnels. When you do computational analysis, neither the particles arrive simultaneously, so ignore that. If you instead use the common theory that the airfoil's upper surface acts like a narrowing venturi tube, the speed increases, pressure decreases, and the airfoil experiences upward force. Well, that's incorrect for several reasons, but one of them, and quite an important one, is that you're only basing it on the idea that lift is being generated on the upper part of the airfoil. That would mean that on the bottom part you could have any geometry and the lift force would still be the same. Of course, that's not the case. And the third incorrect theory is the typical one that says the airfoil is moving and the air is hitting the airfoil and bouncing off. This is completely incorrect for subsonic flight because, as I've said several times, I'll leave you a link, for example, there the air. When an object moves at subsonic speeds, the air senses the pressure waves of an object that's moving. So air is displaced before the object arrives. So the air would never ever collide with the airfoil. But we can also say that it's incorrect because we're simply assuming that the lift force is being generated on the underside of the airfoil. Therefore, just like in the second case, we could put any geometry on the top and the lift force would still be the same. Of course, this is incorrect, but there's something very important to say here. And that is that this theory of air bouncing is actually used for hypersonic flight, but for super high Mach numbers. For subsonic flight, definitely not. That doesn't explain a commercial airplane, not even as a joke. So do you know what? Three explanations you should never use to explain the lift force in airplanes. So now, let's see which ones you can actually use to explain lift. There's something important here, and it's different if a friend, like a lawyer, asks you while having a beer at a bar, "Hey man, why does an airplane fly?" That's not even close to the same as having a conversation between engineers and discussing what the real reason for lift force is. You can't explain as much to your friend as to an aerospace engineer. Let's split the explanation of why airplanes fly into a short and a long answer. You'd give your friend the short one. But if, on the other hand, you ask me, please, I really want to understand. To fully understand lift, I'd have to give you the long answer. Here's a quick answer. Why does an airplane fly? I'll explain both in this video. If you've been following me on this channel for a while, you already know my answer will always be, I'd say, the short answer. Airplanes fly because they deflect air downward. That's no surprise to you. If you follow me, you already know that. But then, what about that? About the difference in pressure on the wing? That could also be a brief answer to why airplanes fly. So if I ask, why does an airplane fly? You say planes fly by pushing air down? That's fine, and if you said airplanes fly due to a pressure difference on the wing, that would also be correct. The issue with the pressure difference, as I've always explained, is that it causes many mistakes. That's why when you ask them for details, they can't provide any. Or worse, when they explain the pressure difference by claiming both particles arrive simultaneously. And that's why, personally, I don't like the answer that planes fly because of the pressure difference, but you can give it. That's why I support the idea that planes fly by deflecting air downward. It's simple enough for even a child to understand. You show a kid a helicopter and they see the air going down, and then with a plane it's exactly the same. It's pushing air downward. Thus, the plane stays aloft. In fact, look, I'm gonna show you some shots with smoke and some paper airplanes so you can see that even paper airplanes clearly deflect air downward. Alright, so what I'm gonna do right now is show you how I know how the air changes. Because of a paper airplane, how it goes downward, I have a lot of paper airplanes that I've made. By the way, this design from the channel of Bola Manuel is a paper airplane expert. Your curiosity is answered with the link provided. We're about to launch, and there will be lots of incense smoke. I'm going to throw the airplane, and we'll see how the air gets deformed. So let's do it. I haven't said this, but don't do this at home because it can get out of control and you could set your whole house on fire. In fact, I actually had to end up pouring water on it. I leave the bloopers on Patreon. So, as a short answer, yes, you can say the airplanes fly either because they're deflecting air downward or because of the difference in pressure. But actually, if we go deeper, we analyze what's really happening. You have to talk about both things, both the difference in pressure and the fact that air is being deflected downward. Because, as you're about to see, both are related and the lift force is not just one or the other, it's both things together. It's super important, you'll understand it now, but the problem comes when someone gives you this short answer to why an airplane flies. They think that alone explains why airplanes fly. But not even close, because, for example, if you tell me that airplanes fly because they're deflecting air downward, then I ask you, why do they deflect air downward? What causes the air to deflect downward? Or, if you say airplanes fly due to pressure differences on the wings, you would change the question from why do airplanes fly to why is that pressure difference created? Because of course, if you answer me that airplanes fly because of a difference in pressure, then I'm gonna say to you, what causes that pressure difference? Well, as you can see, it's something that's not easy to explain and not many people really understand what's actually happening. Everyone wants to know why airplanes fly. In fact, the downward deflection of air and the difference in pressure on the wing are linked, they go together. You can't have one without the other. And that's a question I've always asked myself. Many followers ask me that on Instagram. I'll share my Instagram and I've answered, are they linked? There can't be any deflection of air without a difference in pressure. So let's dive right into the long explanation. Let's start with the downward deflection of air. Why does air deflect downward? On the airfoil's underside, it's clear, the air just arrives. It hits the airfoil, adapts to its shape, and exits mostly downward. That's simple, but what happens on the top side? Why does the air stay attached there? The truth is, it doesn't always stay attached on top. Sometimes it doesn't. Of course, this isn't the optimal case for an airplane, but lift is still being generated there as well. Don't think that's not the case, but now comes the question for the other cases, for the cases where it does. That the air is staying attached on the top part. The top part, why is it staying attached? That's the key. What actually keeps air attached to the top of the airfoil? A lot of people here would talk about the Coanda effect, but you can't use the Coanda effect here. I didn't know that a few months ago. In fact, I think I've messed up on the channel before by saying that. It doesn't take off due to the Coanda effect, but we can't discuss the Coanda effect here since it's the only topic allowed. When air comes out of a nozzle, for example, when you blow or when you're using air from a hairdryer, that's because the total pressure of the air from the nozzle is higher than the total pressure of the surrounding air, and so it tends to stick to a surface. But this doesn't happen on an airplane wing, because on an airplane wing, of course, there's no nozzle blowing air over the top. If you don't believe me, look up the Coanda effect online. It's only mentioned with jet flow, which is what I'm discussing with a nozzle. But then, why the heck does the air curve? And what do they do to explain why the air curves on the top part of the airfoil? They assume air has no viscosity, which isn't true. It does have viscosity. It has low viscosity, but it has so little viscosity that we can really assume it doesn't matter. So we assume a non-viscous flow, so when we're talking about non-viscous flows around an airfoil, there's a very important thing, which is what's known as the Kuta condition, which is that the air absolutely has to leave. When we're talking, mind you, about fluids that have no viscosity, the air absolutely has to leave. Parallel at the airfoil's top and bottom, this is called the Kuta condition. So of course, when flying at low angles of attack, like 2 degrees, this is going to be fulfilled almost perfectly. We could say that the Kuta condition is being met. But remember, air has viscosity, so as you keep increasing your wing's angle of attack, it starts to separate at the back. At the end of the airfoil, the air begins to separate, and this is because of viscosity. But when we're at low angles of attack, the Kuta condition is indeed met. So, we could say that on the upper part, the air is not separating because the air has very little viscosity. So for cases where we're at low angles of attack, it's as if it were a non-viscous flow. And when we have a non-viscous flow, the Kuta condition must be met no matter what. The air absolutely has to follow that curve. If you give it too much angle of attack, viscosity causes the flow to separate, starting at the back and moving forward until all the air separates at the back. One very important thing for you to understand now is that when the air goes downward over an airfoil, lift is being generated. The lift force is produced at the moment when the air changes direction, at the moment when the air turns, not at the end of the airfoil. At the end of the airfoil, the air simply exits. It isn't turning. Lift is generated when the air is changing direction, that is, when it is curving, which usually happens at the front part of the airfoil. That's why the aerodynamic center is important. If you don't know what it is, check out that video. It's at 1/4 of the chord. It's in front. We've already explained Dan Walsh. Why does the pressure difference happen when air is deflected downward? Even better, how does the pressure difference relate to the downwash and the downward deflection of air? Well, it actually has everything to do with it, because for the air to turn, there needs to be more pressure on the outside of the turn than on the inside. Because of Newton's first law, the law of inertia, the air just goes straight, that's it. But the only way for the air to turn is if there's more pressure on the outside of the turn than on the inside. Therefore, more pressure is applied on the outside and the air ends up turning. This is what happens in a tornado. On the inside, the pressure is very low. However, on the outside, the pressure is much higher. And as you go from the outside to the inside, the pressure decreases. You can see it, for example, with this graph. As you get closer, the pressure decreases a lot. So on the lower part of the profile, the air curves more or less like this. A pressure gradient is needed for this to occur, similar to a tornado. And since the air is curving more or less like this, the center of the circle would be more or less around here. So pressure increases as you move away from the circle and decreases as you get closer. But the opposite happens on the top part of the profile, where the air curves like this. And for this to happen, the part closest to the profile has to have less pressure, because it's the one closest to the center of the circle. We can roughly say it's here if the airplane wing moves through the air. And from what I just explained, we know that the pressure on the top part of the profile has to be lower than far away and far away. The pressure is atmospheric pressure. This means pressure on the top must decrease while the bottom experiences the opposite. If we know there's more pressure at the bottom than far below, and that far below, the pressure is atmospheric pressure. So here, the pressure at the bottom of the profile must increase. And that's why they are completely connected. The air's downward turn and pressure differences on the wing. So I think now you really can understand why airplanes fly. You can give both the short answer and the long answer, but above all, please understand it. Don't give an answer without really understanding it. Never use the 3 explanations I gave you at the beginning. The 3 explanations, wrong ones from the lift force. Forget about those completely. Notice I didn't have to do anything like that. And remember that we can't use the Coanda effect to explain that the air isn't separating on the upper part of the airfoil. Well, Yankee, I hope you really understood this video, that you liked it. If that's the case, give this video a big like. Share it with friends, family, or anyone interested in space engineering, even your engineering professor. If you're studying engineering, let's see what your fluids professor thinks about it. Everything I've said is based on this book, which you can see on the screen. But anyway, it's a combination of all the books I've read, but this one is definitely the most complete I've seen about lift force. That's it, Yankee. Share this with the friend who says airplanes fly, because particles arrive simultaneously. Seriously, we have to put an end to the myths about lift force, and you have to help me put an end to them. Share your thoughts and favorite explanation in the comments. Have I taught you something you didn't know? I certainly have learned a lot in these past few months while researching this topic. If someone had shown me this video a year ago, even though I already knew a lot about lift force, I still would have been amazed. So I'll upload the next video, a small continuation of this one, talking a bit about flaps, about slats. Why do they generate more lift? Do they create more drag or less? In about 2 months. Unless you smash that like button, and for example, we reach something like 1,500 likes, which would be absolutely crazy. But that would mean you really like the video and want more on that topic. I'll leave the reference links below that I used, so you can check my sources. And well, if you want to contact me, you can do it through Instagram or LinkedIn. Subscribe to this channel, and then you can watch this video here. Yankee, it's always about solid science above all.